Hi, my name's Mr. Ray. This video is about climate change. I first started looking into climate change when I was a high school astronomy teacher, and I was looking for a way to terraform Mars. I wanted to do a unit with my students and show them what it would take to terraform Mars. And what I wanted to do was add an ocean to Mars and then add an Earth-like atmosphere and then see how much carbon dioxide it would take to add to that atmosphere, or how much Mars would need to warm it up to Earth-like temperatures, because Mars is much colder than the Earth. And so I thought if we add enough carbon dioxide, it would warm the atmosphere. So I looked over the internet and I looked for an equation that would tell me exactly how much carbon dioxide I would need. I also did some tests with carbon dioxide and air mixtures to try to come up with an equation that would tell me exactly how much carbon dioxide was needed to raise Mars's temperature. Well, as I began to research and experiment, I began to discover some things that totally changed my view of climate change and the greenhouse effect. And I want to share those things with you in this video and in some further videos that will explain the things that I found. The title of this video then is going to be The Giant Greenhouse Math Mistake, and we're going to start with that. If you're at all familiar with climate change, you've probably heard of the greenhouse effect. And the greenhouse effect is that there's certain gases in the atmosphere that can absorb certain wavelengths of radiation coming off the Earth. Those gases are said to be then increasing the Earth's temperature 34 degrees Kelvin, which is 61 degrees Fahrenheit. So sunlight comes down, it warms the Earth then tries to release that heat into space. Greenhouse gases intercept some of that heat, and it's said that greenhouse gases warm the atmosphere 34 Kelvin degrees or 61 Fahrenheit degrees. Now the average surface temperature of the Earth is 288 Kelvin or 59 degrees Fahrenheit. And so without greenhouse gases, our temperature would be 254 Kelvin or -2 Fahrenheit. The temperature 254 Kelvin is known as the Earth's blackbody temperature. If the Earth was a perfect blackbody, a perfect absorber of radiation and a perfect emitter of radiation, then it's said that the Earth's blackbody temperature would be 254 Kelvin or -2 Fahrenheit. From now on, I'm just going to talk in terms of Kelvin, but I wanted you to see the Fahrenheit equivalents. Unfortunately, the idea that Earth's blackbody temperature is 254 Kelvin, that's based on a calculation method error. What they're using to produce this is average radiation. They look at the amount of radiation that impacts the Earth, average it across the whole Earth's surface, and then use the average radiation to derive an average blackbody temperature. Blackbody temperature would be the energy from the sun alone. The mathematical reason why you cannot take average radiation and come up with average surface temperature is that radiation is a fourth power of temperature. So here's the formula for that. Radiation is measured in watts per square meter, and it's equal to the Stefan-Boltzmann constant, which is a decimal point with 7 zeros, 567, times temperature in Kelvin to the fourth power. So you can see from this equation that radiation is a fourth power of temperature, also multiplied by a constant. You cannot average fourth powers to find the average roots of those fourth powers. Let's take 3 and 5 as an example. All right, so 81 is the fourth power of 3. 625 is the fourth power of 5. If you average the two fourth powers, you come up with 353. Add them up and divide by 2, you get 353. Now the fourth root of 353 is about 4.33. And that's too high to be the average of these roots. These roots, the average of 3 and 5 is 4.0. and 4.33 is too high to be the average of those roots. So you cannot take the average radiation and derive a average surface temperature from it, just like you can't take the average of fourth powers and come up with the average of their roots and derive the average of their roots from it. So you can't take fourth powers and derive the average of their roots from it. Now, you say the mistake here is small, but when we get into real temperatures and real radiation amounts, you're going to see that error magnified. So for instance, if we take 10 degrees latitude on a black body Earth, at 10 degrees latitude, the amount of radiation is going to be 930 watts per square meter. That's what's not reflected. That's what's absorbed by the Earth. Okay, at 10 degrees latitude, this is the amount of radiation that would be absorbed by the Earth. That corresponds to a temperature of 358 Kelvin. Make sure you can see that. Oh, not quite. Okay. All right, so 930 watts per square meter at 10 degrees latitude corresponds to a temperature of 358 Kelvin when you put it through this formula. Then take the radiation at 75 degrees latitude, or any other latitude you want, and at the end of this video I'll show you how to compute the radiation at each point on a spherical black body, the same distance from the sun as the Earth is. But I'll get into all the math at the end of the video. But for now, 75 degrees latitude would produce 352 watts per square meter of radiation coming from the sun, and that would result in a temperature of 256 Kelvin when put through the formula. So here we have one point on the Earth's surface at 10 degrees latitude, 930 watts per square meter at noon, okay, and then 75 degrees latitude at noon, 352. Now, if you take the average radiation here, the average radiation between those 2 points would be 641 watts per square meter. So the average radiation, add those up and divide by 2, you get about 641 watts per square meter. And that would result in an average temperature of 326 Kelvin. So if you average the radiation, you would expect the average surface temperature to be 326 Kelvin. But if you add these two up and divide by 2, the real average is only 307 Kelvin. So you can see the real average surface temperature on a black body is much lower than you would expect if you first average the radiation and then try to derive the average surface temperature. You end up with something that's too high. Now, this becomes even more extreme when you factor in temperatures on the dark side, on the side away from the sun. So the sun's shining on one side of the black body. On the other side of the black body, there is no sunlight coming in. And so you have to factor that into, no matter if you're taking the average surface temperature, you have to factor in the dark side as well. So now we'll look at a dark side temperature. Okay, so the dark side temperature is going to be zero, has zero radiation because it's blocked from the sun, and so it has a black body temperature of 0 Kelvin. So if we take a point on the light side at 10 degrees latitude and average it with another point on the dark side, well, if we average that radiation, the average radiation would be about 465 watts per square meter. And that, if we then try to derive the average temperature of those 2 points, the average temperature would be 301 Kelvin. So if we average the radiation first and try to derive an average temperature from that, the average temperature would be 301 Kelvin. But if we take the real average temperature, The real average temperature, when you add these two surface temperatures up and divide by 2, is only 179 Kelvin. So you can see that the magnitude of the error is increasing when we factor in the dark side. And this is why the idea that the Earth's temperature is 254 Kelvin is an error, because what they're doing is they're averaging all the radiation points. Okay, all the points of radiation they're averaging first and then deriving an average temperature from that, and they're always going to come up with something that's too high. So this is a calculation method error, okay? And it's based on the idea that you cannot take the average of fourth powers and derive an average of the roots. Now, when the wrong method is used and they average radiation first and then try to derive the average surface temperature from it, that's where they come up with the idea of 254 Kelvin being the black body temperature of Earth. It's based on a wrong method of calculating the average surface temperature. This is too high. When you take every single point on a black body sphere and you average it point by point, it only comes out to 143 Kelvin. So this is the correct black body temperature, because it's done in a point by point method, including all the points on the dark side, all the points on the light side. You'll come up with an average of 143 Kelvin, and I'll show you at the end of the video how to do that math. So what does that tell us about global warming or the greenhouse effect? What that tells us about the greenhouse effect is this. We were thinking that the greenhouse effect raises the temperature from 258 to 288 Kelvin, so that there is 34 degrees Kelvin of greenhouse gas warming, all right, or of global warming so far, 34 degrees Kelvin, to go from the black body temperature as it's calculated up to the average surface temperature of Earth. The reality is something is warming the Earth not from 254 Kelvin up to 288 Kelvin, but something is warming the Earth from 143 Kelvin all the way up to 288 Kelvin. So instead of 34 degrees of warming, Earth has to be warmed 145 degrees Kelvin. And 145 degrees Kelvin is much too much warming to attribute to any kind of greenhouse gases effect. So the idea that greenhouse gases warm us 34 degrees is based on a fictional black body temperature. The real warming is from 143 Kelvin all the way up to 288 Kelvin, and there's a different mechanism that has to do it because greenhouse gases are not powerful enough to do that kind of warming. There is a different mechanism that is powerful enough to do it. Before we take a look at that mechanism, though, there's another fact that we have to include. All over the Earth, the average rainfall is 990 millimeters. Okay, 990 millimeters of rainfall. Before that rain falls, it starts out as liquid on the ground and it has to be evaporated into the atmosphere. The rainfall first has to be evaporated. In order to get 990 millimeters of rainfall, the water first has to be evaporated from the surface, okay? And when water is evaporated, it absorbs extra heat energy called the latent heat of vaporization. So heat energy is absorbed from the surface, then the water vapor travels up, releases that heat at the level of the clouds away from the surface to go back to being a liquid, and then falls as rain. So in order to get 990 millimeters of rainfall, you first have to evaporate all that water, and that carries heat, that cools the surface and carries heat and releases it away from the surface. When you calculate how much it takes for 990 millimeters of rainfall annually over the whole surface of the Earth, you find out that the Earth is being cooled 192 degrees. There's 192 Kelvin degrees of cooling that's happening to evaporate all that water at the surface and turn it into vapor so that it can rise up, release the heat away from the surface. That results in a total cooling, an average total cooling of 192 Kelvin, and this is constant cooling. So there's an average constant cooling going on of 192 Kelvin. To get to 288 Kelvin, we not only have to go up 145 degrees, but we also, the Earth is being constantly cooled 192 degrees. We have to go up another 192 degrees so that evaporation can constantly cool it back to its average temperature. So not only do we have to go from 143 up to 288, we also have to go 192 degrees further and come back down via evaporation. So evaporative cooling is bringing us down 192 degrees from another temperature. And so we need a heating mechanism that not only heats us 145 degrees, but we need a heating mechanism that takes us all the way up to this level so that 192 degrees of constant cooling can bring us back down to our average temperature. And so there is a heating mechanism that can do this for us, but it's not the greenhouse gases. Okay, what could be heating the Earth up from 143 Kelvin way up here so that evaporation's cooling it back down to its average temperature of 288? What could create that amount of heating? More than 145 degrees Kelvin, more than 34 that they attribute to greenhouse gas. We know from physics that if you compress gases, they heat up. What's compressing the Earth's atmosphere? Gravity is compressing the Earth's atmosphere. The gravity squeezes the Earth's atmosphere so much that 78% of the atmosphere is in the bottom 11% of space. So gravity is actually pulling the air down, squeezing it so that you have high pressure at the bottom. How much does the gravity heat the air by compressing it? How could we figure that out? If we switched off gravity, the atmosphere would fly out into space. So let's first assume that we've got a lid around the atmosphere. Okay, so let's put a lid around the atmosphere. It doesn't let any energy in, doesn't let any air out. Now if we switch off gravity, the whole atmosphere is just going to spread out evenly inside this container. Now if the atmosphere spreads out evenly, how high is this container? Well, the internationally accepted boundary of space is 100 kilometers. Okay, so if you take the atmosphere and you look at 100 kilometers of it, okay, 100 kilometers of the atmosphere. You turn off gravity and the atmosphere would spread out evenly, the temperature would average out, okay, so you'd balance out to the average temperature, you'd balance out to the so how do you calculate, how do you figure that out? Well, I took the U.S. standard atmosphere, take the United States standard atmosphere in 100-meter increments, okay, took the average pressure, the average temperature, you can figure out the number of molecules in the air. So each one of those then has an average, each layer, each 100-meter layer. I figured if I took it in 100-meter increments, well, about the length of a football field, there's not much difference between the air at the bottom of that football field to the air at the top of that football field of 100 meters. And as a result, I think those are pretty good increments. You can do it, again, you can do it with calculus, smooth out all the increments. But what I did was I took the U.S. standard atmosphere in 100-meter increments, figured out the average pressure of each layer, the number of molecules in each layer, the average temperature in each layer. And then when you finish it out, if you turn off gravity, the atmosphere is going to spread out. All that stuff is going to average together. So you take the number of molecules, their temperature and pressure of each one of those molecules, average it all together, And here's what you come up with. The average pressure of the atmosphere that I calculated is about 7,139 pascals. That's the unit of pressure. So 7,139 pascals. The average temperature is at 250 Kelvin. That's the average temperature of the Earth's atmosphere if you calculate it that way. So if we have a starting temperature of 250 Kelvin and a starting pressure of 771.39 when gravity is turned off, how will that change when gravity is turned back on? Well, when gravity is turned back on, you're going to get a sea level, and we're talking about surface pressure, that's what we want. Sea level pressure with 101,325 pascals. So if we go from 771, if we go from this pressure to this pressure, we want to know how would this temperature change and what surface temperature would we get? Well, there's a formula for that. The temperature, the second temperature that we want to find out, that the temperature that's produced, okay, is equal to the first temperature. That's multiplied by the ratio of pressures. The second pressure, that's the final pressure right here, divided by the starting pressure, okay? And then it's got to be raised to a power. And the power that it's raised to is itself a ratio. It's y minus 1 over y. And what that y represents is, that is the heat capacity ratio. So how much, heat capacity is how much heat it takes to raise something 1 degree. So this is the heat capacity ratio for air, which is Cp of air divided by the Cv of air. If you look those up on the internet, you can find them. For air, this whole thing equals about 1.4. So what we're going to do is we're going to take the pressure divided by, this pressure divided by that pressure, raised to the power 1.4, that's what this ratio would come out to be. Okay, and then multiply it by the starting temperature of 250 Kelvin. Okay, and what you get is, what this equals is 534 Kelvin. What that tells us is that gravity should be raising the surface temperature. If you spread all the energy out evenly, and you turn on the gravity is going to drive that temperature up to 534 Kelvin. Now I'm going to call that the gravitational pressure, because it's pressure caused by gravity. Gravitational pressure temperature setting. The gravitational pressure temperature setting for Earth, 534 Kelvin. Okay, that is the temperature that, well, you say, well, we only have an average surface temperature of 288 Kelvin. Well, that's right. We've got 192 degrees of cooling going on just from evaporation. So let's take a look at that. Let's take a look at that. We have a black body temperature of 143 Kelvin, a true black body surface temperature of 143 Kelvin. We have an average surface temperature of 288 Kelvin. We just found out that gravity can raise the temperature. Gravity squeezing the atmosphere should raise the temperature up to 534 Kelvin, but we already know that there's something that's cooling it. So there's something that's cooling it from here, 192 degrees from evaporation. Well, 534 down to 288 is not 192, it's a little bit more. So where does the additional cooling come from? Not only is the surface temperature cooler than expected from pressure, okay? Not only is surface cooler than expected from pressure, but the upper atmosphere is hotter than expected based on pressure. All right? Because it's thinned out up here. This should be a lower temperature. This goes from the average of 7,000 pascals down to, you know, less than 1 Pascal in some cases, what's trapping the heat up here? What's intercepting radiation? Some of the radiation that's absorbed isn't reaching the ground. Normally, if all of the radiation was spread out evenly and gravity squeezed it, we'd get 534 Kelvin. Ozone. Ozone intercepts some of the radiation so that it never reaches the ground. It prevents it from heating up to what gravity would heat it to. It prevents it about 3 degrees. So with ozone, we get about 3 more degrees Kelvin. Well, there has to be something to get us all the way down to 288 Kelvin. We need about 51 more. We need about 51 degrees to get all the way down. Well, what could cool the Earth 51 degrees more? If pressure is taking us up to 534 Kelvin, evaporation is constantly cooling us 192 Kelvin. Ozone is causing the upper atmosphere to be warmer than expected, so some of the energy is prevented from getting down. We get 3 degrees prevented from ever getting down there. What about the 51 degrees? What could be left? Well, some of the precipitation, some of the 990 millimeters of precipitation is frozen precipitation. What happens to frozen precipitation when it reaches the ground? Well, when frozen precipitation, snow, it can include snow. So areas where it snows, it can include sleet, and it could include hail. And hailstorms, hail can be produced anywhere on the earth. Any thunderstorm on the earth can produce hail. And so what happens when snow, sleet, or hail reaches the surface of the earth? Well, it has to, when it eventually melts, okay, otherwise the snow would continue to build up, until, the glaciers would be getting bigger instead of smaller. But what happens when the snow hits the ground? It stays there for a while, okay? But when it melts, it has to absorb extra heat energy to melt, cooling the surface further, okay? Now, some areas worldwide, how do you find out how much snow, how much frozen precipitation is happening? Well, you have to look at snow records. And so I went through and I tried to find all the snow records in Canada, and the stations are not spread out evenly. There's some stations that are miles away from other stations, and then you have clusters of stations all in the same latitude and longitude area, So you have clusters of stations. You have to figure that those are going to pretty much take an average of that one cluster and count it as one data point, and then you've got to, so we don't have complete coverage of how much snow falls on the earth. I looked at Canadian records, looked at U.S. records county by county, and tried to get up an average amount of snow each year. Then you look at Asia, and it's the records in Asia and Russia and Europe are even more spread out. Okay, and then you've got regions of the world, South America, in the southern hemisphere, and then you've got areas in the earth that get snow that are in tropical areas, but they're at high elevations. So you've got Tibet, you've got other places like that where you have to take into account the snow, and we don't have complete records. We don't know how much snow falls over the South Atlantic, for instance, between Antarctica. We know how much falls on Antarctica, or we have an average anyway, and we know how much falls in the Arctic. We don't know how much falls over the ocean between Antarctica and the continents, or between in the North Pacific Ocean or the North Atlantic Ocean. How much snow is just falling over the ocean? It still has to melt, and it still helps cool the surface. So how many degrees? Well, the more of those data points that you include, the more areas that you can cover and that you can calculate, Some areas have not been measured, but when you look at the measured areas, it shows the right amount to have 51 more degrees of cooling. Now remember, this is a known mechanism. To heat things by compressing them, that's a known mechanism. If we apply that to Earth's atmosphere, the surface should be 534 Kelvin. It never reaches 534. In other words, there's enough compression to produce that, but it never reaches that because there's a constant cooling of evaporation, and this is exact. This we can know for sure. Okay? There's a constant cooling of at least 192 degrees. Then we have ozone. If you took the heat that's in the upper atmosphere and spread it out evenly, it would heat the surface 3 more degrees. So we're being prevented from heating 3 degrees. And then 51 degrees, and all of the measurements that we do have point to the right amount of cooling to bring us down to 288 Kelvin. So instead of trying to figure out from 254 Kelvin to go up to 288, when we take a look at the real black body surface temperature and realize that there has to be a mechanism that puts us up to here, and we have pressure generated by gravity that can take us all the way up here, then we start wondering, well, what's cooling us off? What's cooling us off is evaporation. The ozone layer is keeping some of the heat above the surface, and then the rest is cooled by frozen precipitation as it melts. Okay. As more and more measurements of frozen precipitation come in, if we can get measurements over the ocean, that should get us closer and closer to pinning this down exactly. But what we do know does point to 51 degrees of cooling worldwide. So what's our conclusion? Our conclusion is 34 degrees of warming from 254 Kelvin. 34 degrees of warming by greenhouse gases is fiction to reach 288 Kelvin, because it's based on a false surface temperature, false black body surface temperature. This is not the correct average surface temperature. Remember, this is surface temperature. They're talking about 34 degrees of warming by greenhouse gases to reach another surface temperature of 288 Kelvin. Based on a false black body surface temperature. You cannot take average radiation, which is what's done, take average radiation and derive and come up with the correct average surface temperature. The correct average surface temperature is 143 Kelvin. Okay? That's the first point. Second point, gravity compresses the atmosphere so that it would set the temperature at 534 Kelvin. So gravity is compressing the atmosphere, and based on the average pressure and average temperature of all of the atmospheric molecules, when gravity compresses that, it should set the temperature at 534 Kelvin. Why? That's point number 2. Heating of the Earth is not by greenhouse gases, it's by compression of gravity. Gravity compressing the atmosphere is what sets the temperature. Why does it never reach that? Well, the next point is it never reaches it because there's a constant cooling of 192 Kelvin just by evaporating in the water cycle. Just by evaporation cools the Earth's surface 192, and it's constantly cooling the Earth's surface 192 degrees. Okay? In addition to that, the ozone is helping the Earth to stay 3 degrees cooler because it's intercepting energy high up in the atmosphere that otherwise would heat the Earth's surface. And finally, the final cooling piece of the puzzle that's bringing us back down to 288 Kelvin is the 51 degrees of cooling from frozen precipitation. All the figures of frozen precipitation that we have point to the right amount, that that there is the right amount happening in order to finish off the 51 degrees of cooling. So that is that is the giant greenhouse math mistake, and this is the first video in a three-part video about this. In other videos, I'm gonna discuss. I'm gonna get into carbon dioxide and radiation. I'm gonna explain it to you. And we're gonna show that, and then we're gonna show the the history of climate change and what the mechanism for climate change actually is. What is driving the climate, and if we have global warming, what's it coming from? And I think you'll enjoy those videos. Hopefully, you'll enjoy those videos as well. And thank you. Now, for the rest of this video, I'm going to get into more detail on the math. Okay, so if you don't want to get any deeper on the math, you're dismissed. Okay, so here we go. How do you calculate point by point the temperature of the Earth? You have to take the radiation that's hitting the Earth's atmosphere. Okay, radiation at the top of the atmosphere. What I took 1361. Okay, 1361 is the radiation watts per square meter. Okay, as the radiation. I got that off the NASA website, or off the NASA Earth fact sheet. All right, so radiation 1361 striking the upper atmosphere. You have to multiply that by how much is actually absorbed versus how much is reflected. And so you got to take the albedo, and what you do is you take 1 minus the albedo into account. And when I take 1 minus the albedo, I get 0.694. So basically you start with 1361, multiply it by 0.694, which is the albedo, and then you have to multiply it. If we're talking about a single point, you have to multiply it by the what I call the cosine of the tilt angle. Okay. When the sunlight's coming straight down to the Earth's surface, you're getting a full blast of radiation. If you take 1361, multiply it by 1 minus the albedo, it comes out to about 944.5 watts per square meter. All right, 944.5. When the sunlight's coming in at an angle, and if you look at the Earth, you know, if the sunlight's hitting the equator, and the Earth is straight up and down compared to the sunlight's hitting the equator, you're going to have no tilt in your angle. But if the sunlight's hitting anywhere else, okay, there's going to be an angle of tilt. And so if the sunlight's coming in tilted here, what happens is it spreads out. This may be the same intensity as this, but when it strikes the surface, it spreads out this much. That turns out to be the cosine of the tilt angle. All right. So if this tilt from, let's say this is 0, if we're 10 degrees tilted, it would be the cosine of 10. If we're 20 degrees, 30 degrees, so you can go by latitude. I call the same thing as a latitude. If this is 0 degrees latitude, there would be the cosine of 0. If this is 10 degrees latitude, the cosine of 10, and so on, all the way up to 90, which was cosine of 90 is 0. And so you'd multiply it by 0. So the cosine of the tilt is factored in. So you can create a spreadsheet, and you can do every angle 0 to 90. So if you take your angle 0 to 90 in one column of your spreadsheet, and then change it to radians, because your computer likes to use radians. Okay, so put radians in the next column. Then take 1361, all right, and so you're going to take 1361, multiply it by 1 minus the albedo, which is 0.694, and then multiply it by the cosine of these angles, of this angle, all right, times the cosine of, and let's say it's the latitude, times the cosine of the latitude. So 0 to 90, then 1361 times this times the cosine of 0 to 90. All right, and that will tell you how many watts per square meter is at each angle. Now I did one for a 30-degree tilt. So for a 30-degree tilt, the cosine comes out to 0.866. So if this was 30 degrees, and then the cosine of that would be 0.866. All right. So 1361 times that, you get 818 watts per square meter coming in at 30 degrees. Okay, and then you want to take that and divide it by the Stefan-Boltzmann constant, which is a point with 7 zeros, and then 567. Okay, so you divide it by that, and then you take the fourth root of that, and you'll get the temperature, the black body temperature at 30 degrees latitude. All right, and you can repeat this for 1 through 90. Okay, and that will give you all the black body temperatures of all the angles from 0 to 90. Now after that, once you have all of the corresponding temperatures from 0 to 90, then you have to apply area to each of those temperatures. Okay, and so for what I did was, in order to compute the area, I did this in 1 degree increments. So for an angle of 1 degrees, I went from 0.5 degrees to 1.5 degrees and used the temperature for 1 degree. All right, so at 1 degree increments all the way over. For 0, I went from 0 to 0.5 was 0, okay? And 0.5 to 1.5 is 1, and then 1.5 to 2.5 is 2. I would assign the temperature for 2 degrees, okay? So you have a temperature for each angle 0 to 90. Now, the surface area of a spherical section. So if you want to figure out how much area, let's say that you have your sphere, you've got the light shining at 0 degrees, it would just be one spot from 0 degrees to 0.5 degrees. And then the 1 degree angle would come next, and that would wrap around there. And then the 2 degree angle, the 3 degree angle, the 4 degree angle, would take this sectional area, and if you tilt this up a little bit, the area of the spherical section, the area that we want to find for each degree is going to be 2 pi times r times h. Okay, the radius of Earth is 6371000.8. Okay, that equals the radius of Earth. All right. H is the height of the section. So if you've got your area here and you're looking at the angle that comes right here, where the sunlight hitting right here, we're talking about this area right here. So an area of a section similar to that, let's say this is 30 degrees, okay? Then you're going to look at the top line, the top boundary of that would be 29.5 degrees, and the bottom boundary of that would be 30.5 degrees. How do you find that slice of area? You take the cosine of these two and subtract them. So you take the difference in the cosines and then multiply it by the radius of Earth, and that gives you h. So h equals the cosine of A minus the cosine of B. Those are your boundaries, absolute value of that, times the radius. Okay? So that'll give you the height, that'll give you the h for this equation right here. Once you know h and you know the radius, then you multiply it by 2 pi, and that gives you the area of this section that you apply to each degree. So if I'm looking at the temperature of the 30-degree angle, I would take the cosine 29.5 minus the cosine of 30.5. Okay? And that's going to equal about 0.87036 minus 0.86163. And that's going to equal 0.00873. Okay, then you got to multiply it by the radius of the Earth, which is 6371000.8. Okay, and then what that comes out to is 55596.8 meters. All right, and that equals h. That's the height of that section that applies to the 30 degrees. So here's Earth. It's coming down, sunlight's coming down, it's hitting the, let's say this is a 30 degrees latitude. And so you're taking an area from where it would hit at 29.5 to 30.5. The height of that area is going to be this many meters. All right. Then you take your 2 pi RH from that, radius of the Earth, 2 times pi times radius of the Earth times h, and you end up with a huge number of square meters. All right, 225 548 419 209.7 square meters. That's the amount of area that you're going to apply the temperature. When you found the temperature for 30 degrees, okay, based on Stefan Boltzmann and the fourth root, then you're going to take that and you're going to apply it to this many meters. All right. So what do? After you find the temperature for each angle, let's go to 0 to 90. So you go 0 to 90 degrees. Then you find the temperature for each of those. Okay? Then you find the area that you would apply to each angle. Okay, so you find the area that you apply to each angle. Then what you want to do is you want to take the temperature times the area for all of those. Okay? And then you sum it up, and then you divide by the surface area of the Earth. And that produces your average temperature. And since these are all black body temperatures, it'd be average black body temperature. And that's how you come up with 143 Kelvin. That is the correct way. All right, that's a correct incrementally if you're going to go by 1 degree increments. So you can go by half degree increments, you can go by any increment you want, or you can do it by calculus. If you know how to do it by calculus, you can smooth out all the increments and find the same thing. You'll find the same thing that I found. Don't forget the back side of the Earth is all 0, okay? And that's why you can take the sum of the front side, 0 to 90, all the areas of 0 to 90 only takes up the sunny hemisphere, okay? And then divide it by the entire surface area of the Earth, and you'll get the average, average black body surface temperature of 143. And so that's how you can do a point by point or an angle by angle. And you can do it with an Excel spreadsheet. That's how I did it. Let's see. I already gave you the formula for compression, raising the temperature of a gas, and you can look up the heat capacity ratios if you need to. So thank you for watching the video. If you feel like this is useful information, I know it changed my mind. It just showed me that the idea that the greenhouse gases warm the Earth 34 degrees is based on a faulty black body surface temperature of 254. The real black body surface temperature is 143, and so 254 is complete fiction. It's based on averaging fourth powers. It's averaging radiation is the same as averaging fourth powers to find the average of the roots, and it's always too high. This is just the first video, and there's a lot more information. in the next two videos that will put the whole picture of climate change together. I know that what I found transformed my understanding, and I hope it does the same for you. Thanks for watching.